Our large area loop calculator is the quick and easy way to calculate what hearing loop drivers and cable lengths are required for your installations. It provides scaled hearing loop layout representation, calculates the current required, has selectable metal loss adjustment, and will automatically calculate a phased array. Its unique metal loss calculator feature enables users to enter readings into the calculator taken on site and provides an exact metal loss result for the site you are working on. This helps to ensure high quality installation and the best performance of the system. When you first launch this software, this is the screen you will see, and this is the Induction Loop Settings page. There's 6 tabs across the top of the page: Induction Loop Settings, 2D View, Cross-Section View, 3D Surface View, Driver Information, Available Driver Information, and a Diagnostics page with some data. First, we select the Induction Loop Settings page. We have a choice of either metric or imperial measurements. For this example, I will be using metric. If you're in the USA, you prefer to use imperial. You can change the settings by just clicking on the drop-down arrow and selecting either metric or imperial. As you can see, if I hover over the box, there's a tip pops up explaining to you some basic information about that box. Here we have some more boxes. We can put in the length of the area you wish to loop, the width of the area you wish to loop, the type of loop you're going to design. Again, clicking on the drop-down box, you can see that you have various options: perimeter loops, a figure of 8 loop, phased array or 222 for the USA, gapped array or multi-loop for the USA, and phased array or 313. For this example, I'll be using a phased array or a 222. The orientation is the direction of the segments of the array. You have common x-axis or common y-axis. Again, as you can see, if I hover over the box, you get a tip box explaining how the layouts will look. For this example, I'll use common x-axis. The loop height is the height at which the cable is installed. For a floor installation, this would be 0. You can double click on the box and add a value, or you can use the arrows to adjust in increments. We're going to do a floor installation, so I'll select 0. The listening height is the height at which the hearing aid or hearing device is located. Typically, for someone sitting down, this would be in the imperial 4 feet, or for metric 1.2 meters. If you are installing a loop in an area where people may be standing and sitting, it's advisable to set a height that is midway between the sitting height and the standing height. For this example, we'll be doing an install for people sitting down. With regards to metal loss, if you're unsure of the metal loss content in the building, click on the information button. This gives you a brief overview of metal loss and how much you should apply as a guide. As you can see, there are various levels: 0 to 3 dB, 3 dB to 6 dB, and so on. And a typical place you might find this much metal loss. Of course, you can add your own value. If you are able to access the building and do a test loop and actually know the amount of metal loss in the building, you can apply that value yourself. For this example, I will apply a value of approximately 3 dB. The resolution is the plotting value of the drawing in the 2D view. I will use medium in this example. You're able to select the cable type. For an installation above a ceiling void, it may be worth using round wire, but for an installation under carpet tiles, it would be more advisable to use a flat copper tape. Again, with the imperial, I have options to choose cable size in American wire gauge. If, for instance, I use a metric, then these will change to a metric cable selection. The feeder cable is the cable that runs from the loop driver to the loop itself. It is important to add the feeder cable length as it adds resistance to the loop. For this installation we will put in a cable length of 50 feet. This is the length of the cable going to the loop and back to the loop driver. The diameter of the feeder cable can be selected. If you are going to use a very long feeder cable, it is advisable to use a larger cable. We will now add our room length and our room width. These two boxes here are the border offset. You can offset the loop cable from the border of the room by entering values in these two boxes. We now have values in all of these boxes. The Loop Visualizer software has calculated how many segments you require, the current that may be required. It displays the length and the width of the segments. This is for the primary loop and the phased loop. It also displays the offset between the two loops themselves. We've not chosen cancellation loops, so there is none displayed in these two boxes. Once we are happy with all the information we've put into these boxes, we can now click Calculate. As you notice, it says please wait while the calculations take place. If we use a lower resolution, the calculation process is quicker. If we use a higher resolution, calculation processes take a little bit longer. Now we can move on to the 2D tab. The 2D tab displays the loop design itself. There are crosshairs on the design that you can move around by dragging or by using these cursor control buttons at the bottom. You can add and remove the cables from the diagram to better understand how the loop performs in the area that you have looped. You can move the cursor to measure the dB level at any given point on the drawing. Place the cursor at a position, let's place it here, and then if we reference this value here, this is dB level at that location. This is at the listening height. If I move the cursor into the green area and then have a look at the value, we can see that it is minus 0.2 dBs. So this is very useful when you may have another room that's nearby and you want to make sure that the level at the distance from the cable to the point where you place the cursor is low enough to be acceptable for no overspill. These X and Y values are the position of the cursor itself. As you see, they change when I move the cursor. You can change the colour of the cables themselves. At the moment we have red and black, simply by clicking on the box and then changing the colour to whichever you desire. To refresh it, just click Add and Remove. With a lower resolution setting, the edges of the loop layout or the diagram would be more jagged. A higher resolution will give a much smoother finish. It also gives a more defined plotting value. We will now move on to the cross-section tab. The cross-sectional view is a slice through the loop itself, and these values are at your listening height. You have an option to view the cross-section parallel to the x-axis or the y-axis of the loop itself. The default section is directly through the middle of the loop in both axes. I can move this cursor to any position along the line and the value is measured from the center of the loop. So if I look at the center of the loop here, it's 0. I move out to between 30 and 35 feet. At the listening height, the value is between minus 16 and minus 17 dB. If I move to the center of the loop, the value is just under 0 dB. This may look quite uneven, but in reality you're looking at just over 1 dB of difference between the peak and the trough across the loop itself. This level would not be noticeable to the ear when listening to a signal. You can move the cursor by just grabbing one of the lines, or you can grab the center point and move it that way. You can also use the cursor control buttons at the bottom of the screen. The position of the cursor is noted here, and the dB level is down the side here. Remember, distance from the center of the loop outwards in both directions. Again, using this cross-section parallel to axis button, we can change it to the Y axis or the X axis. We can also move the slice of the cross-section to a different location. At the moment, this is showing the distance from the center at 0.15 feet. By clicking these buttons, we can actually move the cross-section through the loop itself. To give you more understanding of this, if I go back to the 2D view, currently we have a cross-section through the center of the loop in both directions. Moving this line is effectively bringing the line towards you if you are looking at this view here, and then moving this line here will bring this cross-section towards you or away from you. We will now move on to the 3D Surface tab. You now have a view of the performance of the loop. There are 4 different views to choose from. We have this one. We have a plan view, a side elevation view parallel to the Y-axis, a side elevation view parallel to the X-axis, and the 3D view itself. You can manipulate this view by just clicking on it and dragging it around to place it in any view you like. Or, as I said before, click on the main buttons down on the right hand side to select the preset views. There is a legend on the right hand side to show you the dB levels at the various locations throughout the diagram. We will now move on to the Drivers tab. In the Drivers tab section, you will see that we have 4 available drivers for your loop system. Using the green up and down arrows, you can select the loop driver that best suits your requirements. There are 6 boxes here displaying different values. The first 2 on the left are the required voltage and the required current to meet the current IEC standards. The next 2 boxes are the available voltage and available driver current. The next 2 boxes are the voltage and current headroom. As we only require 8.7 volts and 2.83 amps, the V34 may be a bit overkill for this loop system. So choosing a loop driver that has less power, less current may be more suitable. As in this case, the V15A only has 15 volts and 5 amps, which is nearer to the required current and voltage. If you're happy with the V15A, you can save a report to your PC by clicking on Save Your Contacta Report. It gives you the option to choose where you would like to save your document. Click OK when you're happy with where you're storing it. We will now move on to the Diagnostics tab. Under the Diagnostics tab, various information is displayed about the loop itself. As you can see, we have the cable lengths, cable resistance, etc., etc. To load a previously saved report, you simply have to click on Load Report. At the moment, these values are all 0, as you can see. If you click on Load Report, navigate to where you've saved a previously saved report and click on it. Click OK. You will now see all the values of the saved report entered into the boxes on the Induction Loop Settings page. Clicking through the various tabs, you will see all of the other information is input as well. If you open the report that is saved on your PC, you will notice that it can be opened in a browser. This is very useful for cross-platform use. As you can see, there's plenty of information on here. It gives you the information about your room length and room width, the type of loop you've used, your listening height, the feeder cable length, the feeder cable type, etc., etc. All the views that you saw on the visualizer are displayed in the report. There is also a dimension layout that can be used for actually laying the loop itself. Information about the driver that you've selected is also included.